Hi, I'm Prof. Joe. This is part of my lecture on measurement technology. Today again talking about some sensory technology, especially about incremental encoders. What is that? Idea is quite simple. It's about measuring distances. And so imagine we have some distance describing tape, kind of a tape marking different distances. And now what we want to do for measuring the distance is counting those lines describing different positions. So by counting those many, we know this is, for example, position 1, 2, 3, 4, 5, 6, 7, 8, 9, position 9. And if those lines have a distance of 1 millimeter, we would know this is 9 millimeters apart. Okay, so idea quite simple, counting distances. And there are different ways of describing those tapes with the lines on it. One would be the optical way. Another would be using magnetism. Both is done. Optically, you can have tapes which let through light in different parts and not marked between the lines, for example, and by that using optical sensor technology to count the lines on the tape. Talking about magnetism, you could have a tape which has north and south poles in a certain distance. So we are defining some period C over here, which for the magnetic case, for example, could be 1 centimeter. And now we need to measure somehow the magnetism. And for that reason, we could use Hall sensors. We already know a Hall sensor 1 and a Hall sensor 2. And now we want to place them in a distance of C plus C over 4 of the period. So not exactly in a period C and not using only one sensor. Why not using only one sensor? Same holds for optical measurement technology also when using optical sensors for counting the lines. Idea is quite simple. Imagine you have sensor A and the sensor B, and now you start to move in a direction. So we will have, depending on the period, signal on sensor A. Let's call it HS8, our sensor A. Now sensor B would, due to the fact that it's 1/4 apart in the period, just be shifted in phase by, so to say, 90 degrees. And that means when going in this direction, sensor A would give us a signal first and then sensor B. But now going in the other direction, so when that's the length, the direction we are going, X. But now when going from the other side, we see our sensor B would give us the first signal and then sensor A, the second signal. That means we need those two sensors to cope with one problem, and that problem is counting up or down. And by using two sensors shifted in phase by 90 degrees, we are able to decide whether to count up or to count down just by looking at the signal and which signal comes first. Great. So we can count our periods. We can count them up and down. One further thing is needed. We need some reference distance. For example, so to say here, and that marks the 0. So now we have the 3 basic units which are great. We know where's the 0, and then we know whether to count up or down in respect to 0. So whenever we start a measurement, we have to do some referencing. That's an important fact about incremental encoders. We need to do referencing. Think of the industrial machinery, which always needs you to do some referencing cycles in the beginning of, at the start of the machine. That's the reason for it, because we have to find the zero for the incremental encoders. And one fact about the magnetic system, which is negative now, would be the accuracy. As I said, for example, those are apart 1 centimeter. One could imagine to place some magnetic tape, or to build some magnetic tape which places those north and south poles in, for example, 1 millimeter distance. But everybody realizes that can't be done in a very high accuracy, in the sub-millimeter range at least. And for coping with that problem, on the one hand, we could use optical systems. Optical systems, we are much more feasible in building smaller lines, and by that increasing the resolution, the accuracy of optical incremental encoder, just by increasing the accuracy of the lining on the tape. That's one possibility, but that possibility also has some limits downwards. Another idea would be to use the behavior of the sensors itself. So let's imagine what a real Hall sensor, or the real Hall sensors would give us. So the north pole comes to the sensor and goes away. That means we have some rising magnetic field, and then the south pole comes along and we have some falling magnetic field. So we get a sinusoidal function normally. Function looking like a sine or cosine. Same holds for the second sensor for sure, but as we all know, we are shifted, and being shifted, we get, it's not very nice, but let's imagine that's a sine, that's a cosine, because sine and cosine are shifted by 90 degrees, as we all know. So we get functions which have defined forms. Imagine the Hall voltage delivered by the Hall sensor 1. We call it U sine, which is some amplitude times the sine in respect to the angle defined by the distance, and that angle is quite simple. We have x, that's the distance itself, divided by the period, so we get the periods in x times 2 pi. That defines us the angle, and on the other hand, we get that cosine function for the other Hall sensor. Again, why is that the cosine? Because we are shifted by 90 degrees. You could do some mathematical calculus and see that we could also write down that this function is the sine of the same angle plus 90 degrees. But that's the behavior of sine and cosine. So let's write it down as sine and cosine at that place. And now we have some more detailed information about our signal. First thing to mention here, one could discuss, hey man, is that a real sine function the Hall sensor gives us? And that's discussable. We have two options for that. We have to design that as properly as possible to approximate that sine and cosine. And moreover, we can just filter non-sine function parts and non-cosine function part out of the sensor signal. That's no problem. We have filter options for frequencies, and so we know the frequency of our period and we can filter for that. So the assumption that this is a usable sine or cosine function is very defined, is very well. Okay, having said so, we can use the assumption of sine and cosine functions. That's legitimate. And now we can think of redefining, using that additional information, the distance. So first thing we can do is we can count the periods. We already have done so by counting the periods. We get a rough distance, but now, moreover, we can use that behavior for defining u sine over u cosine, which equals the amplitudes times the sine of the signal over the cosine of the signal. And now by that we see that's nothing more than the tangents of that function. And now we get the idea. We can do a derivation which says x over c times 2 pi equals the arctangents of our voltage, sine voltage, and our cosine voltage. And that indeed gives us access to a more detailed position, because now we can simply calculate the numerator over the denominator and build the arctangents of it, and by that get a detailed position within one period. This is called interpolation. And that's a simple derivation I gave you here. It's not very complex, but it gives you the idea of how to define very precise positions using interpolation and using sensory signals, which give us a sine and a cosine function. Okay, those incremental encoders are used in a wide variety of applications in industry. So for example, those magnetic tapes are very robust to dirt. Yeah, it's magnetic as long as it's not metallic magnetic stuff, which is the dirt. There's no problem about some dirt, which is in contrast to the optical incremental encoders, which have some problems with the dirt and so on. But for sure, those have no problems with metallic dirts and so on. So whether to choose which incremental encoder to use depends on the application in industries. On the other hand, we have a simple and precise way, due to the interpolation, to define long distance measurements. So, in contrast to the strain gauges, which are very usable for measuring very short distances and distance changes, those incremental encoders are very good to measure large distance changes, in contrast to the strain gauges. Having said so, altogether, incremental encoders are important and simple at the same time, again defining a very good sensoric measurement device for distances. See you next time.